In the last video, we talked about balancing an equation. In this video, we're going to talk about using an equation. We're going to start with limiting and excess reactants, because those are very important to know. Unfortunately for that problem, we cannot use this equation, but what we can do is we can flip it around. We can say oxygen plus 2 hydrogen, oxygen plus 2 hydrogen plus 2 hydrogen are going to form 2 molecules of water. So 2 molecules of 1 molecule of oxygen and 2 molecules of hydrogen are going to form 2 molecules of water. And once again, we see that this is a perfectly balanced equation. Limiting an excess reactant. Imagine if we were going to, if we owned a restaurant, say, and we had plates and steaks. Obviously, every steak needs a plate, and since that's the only thing we have on our menu, every plate needs a steak. But remember that, and let's say that we're giving a good deal, and 2 steaks go on every plate. So 2 steaks are going on every plate, not just 1. 2 steaks. This is important here. Now, what if we have 50 plates and 50 steaks? We have 50 steaks and 50 plates. Well, if we take 1 plate, we put 2 steaks on it, we ship it off. We give it to our customer. We take 1 plate, we put 2 steaks on it, we ship it off to our customers. We're going to run out eventually, because remember, for every 1 plate that we use 2 steaks. So in that case, the number of steaks is going to be our limiting reactant. How? Well, think about this. What if we were to convert 50 steaks? If we were to take 50 steaks, I'm just going to abbreviate that with S, and we want to convert them to see how many plates we would need. Well, we know that for every 2 steaks, we need 1 plate. And so if we cancel out the steaks, we find that we need 25 plates, which is great because we have 25 plates. So we're all happy. But if we convert the other way and we convert from plates to steaks, we find that if we do 50 plates, which is the number of plates that we have, and we convert that into steaks, every 1 plate takes up 2 steaks. If we multiply that across, we need 100 steaks for every plate. So that is sad. And since we have 50 plates, then we need 100 steaks, which we don't have. So nope. Steaks is the limiting reactant. We're going to run out of steaks first. Now, the limiting reactant tells us a whole bunch of things. First thing, it tells us that, 1, we need to buy more. If we want to produce more of the product, we're going to need to buy more of that 1 reactant. If we're going to need to react some more, if we want to fully use up the other reactant. Next, it tells us how many of that product we're going to be able to use as a result of not having enough. We'll be able to tell how many steak and plate platters we're going to be able to serve up if you only have 50 steaks. We'll only be able to serve up 25 because that's when we run out of steaks. Now, if the steaks was the limiting reactant, then the excess reactant is whatever is going to run out last, which is going to be the plates. So let's find out the limiting reactant here. Now remember, to find that out, you're going to need the amounts of both that you're reacting. This is not going to give you the limiting reactant because this is a perfectly vast equation. If you gave me 1 mole of oxygen and 2 moles of hydrogen, I would be able to perfectly react to these. So say I gave 50 moles of oxygen and 25 moles of hydrogen. Now, here's the interesting thing about eliminating an excess reactant. You can only find out those if the units are in moles. The units must be in moles. So if you're given 50 grams, you'll need to convert those to moles in order to analyze the limiting and excess reactants. 50 moles of oxygen is we're going to choose oxygen to convert to hydrogen. If we convert 50 moles of oxygen to moles hydrogen, so moles oxygen, moles hydrogen. We know that for every 2 moles of hydrogen, we need 1 mole of oxygen. We cross off our moles of oxygen, and whoa, we need 100 moles of hydrogen in order to complete this reaction with what we're given. But we don't have 100 moles, we only have 25. The chemist horribly screwed up our order. So we're going to need to, unfortunately, call that hydrogen is the limiting reactant. Because we have plenty of oxygen. All we need is about 13 moles of oxygen. So unfortunately, hydrogen is the limiting reactant. So the limiting reactant is hydrogen, and that by default means that oxygen is the excess reactant. The empirical form. Okay, let's do the theoretical and percent yield. This is actually quite simple. This is just saying that if given this amount of reactant, how many of this amount of product how much of this product will I be able to create? I'm going to go ahead and use this example up here. However, if you're given 2 reactants and 2 amounts, you'll need to find the limiting and excess reactant, and then use the limiting reactant to find the theoretical yield. So I'm going to say that I have been given 5 moles of H2O, water. Now, if you're given 5 grams of water, then you'll need to convert this to moles to be able to use it in the chemical equation. So, 5 moles of water, and we need to convert that, and we need to find out how much oxygen are we going to create. There are some scientists who want to know, hey, if I take 5 moles of water, will I create enough oxygen for everyone in the world to breathe forever? Chances are no, but let's find out. Let's find out what this scientist is going to get from this. So if I take 5 moles of H2O and I convert it to moles of oxygen, and I convert it from moles of water to moles of oxygen, I will see that for every 2 moles of water, I create 1 mole of oxygen. So, unfortunately, Mr. Scientist, you will not be able to create enough oxygen to have the world breathe forever. Instead, you'll probably create enough oxygen for 1 person to breathe 1 time. 1 mole, you'll only create about 2.5 moles of oxygen. However, we're not done yet. 2.5 is not within the significant digits. Remember, 5 okay, so in order to account for that, we're going to need to probably round it up. So 3 times 3 moles O2. But chances are you won't have to round it up that much. There'll probably be a 5.0 moles of oxygen there. Now, the scientist, this is the theoretical yield. However, the scientist actually got only 1.5 moles. He only got 1.5 moles during the experiment. Something must have gone horribly wrong. Let's find out his percent yield. So percent yield is equal to actual yield. I'm going to abbreviate that with AY over theoretical yield. I'm going to abbreviate that with TY times 100. Calculate the percent yield. So if I take the actual yield, 1.5 moles, and I divide that by the theoretical yield, 3 moles, I will get 1.5 divided by 3 is 1/2, or 4.5. Multiply that by 100, I get 50%. The actual yield was 50% of his theoretical yield. So he did not conduct his experiment very well. The last thing in the stoichiometry review marathon is empirical formula. The longest process, however, the most interesting. The empirical formula, if I take a compound C6H12O6, this is it's in what's known as the molecular formula, meaning that its subscripts cannot be simplified. C1H2O1 cannot be simplified any further. That is the empirical formula state. Please note that it is very easy. Anyone can determine the theoretical or the empirical formula from the molecular formula. However, it's very hard to go from molecular or empirical formula to molecular. So remember that a way that you can remember that is M to E. It's very easy to spell me. Easier to spell me than M. It's easier to spell me than M. Molecular to empirical, easy, then empirical to molecular, because you don't know how many times you have to multiply, or what the multiplier factor is. However, it's very interesting. You can go from giving the percent of composition to finding the formula. It's very easy to do that. To do that, all you have to do is find out if you assume there are a certain amount of steps that you have to do. This is a very long process, but actually it's quite easy. Step 1. Assume 100 grams of the sample. This I'm going to actually put in a dotted red box, because you might not have to do this. If they give you the percent composition, then if they say they have a compound is 2.4% carbon, to do that you just assume that 100 grams of the sample, so then you'd have 2.4 grams of carbon. However, if they give you 2.4 grams of carbon and not the percent, then you don't have to do this step. Let's continue on. Step 2. After you assume 100 grams of the sample, the next thing that you are going to want to do is convert to moles. So you're going to have several things that you've now converted into grams. Grams need to go into moles. So if you're given 2.54 grams of carbon, you'll need to convert 2.54 grams of carbon into moles of carbon. This next step is kind of confusing. Step 3, divide by the smallest mole. Well, now that's quite interesting. That's very interesting. How are you supposed to? What is that supposed to mean? Well, say you converted. A compound has 3 elements. You converted them. You have one as a molar, as 1 mole. The second element as 2 moles, and the third element as 3 moles. So the grams to mole has become 1, 2, and 3. Now you would divide each number by the smallest mole, which would be 1. So 1 divided by 1 is 1, 2 divided by 1 is 2, and 3 divided by 1 is 3. And from here, you've gotten to the empirical formula. So if you have, now, like I said, 1, 2, and 3, it would be x1, it would be x1, y2, z3. So you're converting to moles, dividing by the smallest of however many moles you got, however many moles of an element you have. You divide by the smallest, and then you get the empirical formula. From there, it's a simple finding the molar mass of the empirical formula and getting the mass of the compound, dividing the two, and then you get the molecular formula, which you'd use to then multiply by the empirical formula to get that molecular formula. So what I mean is, if you're given if they tell you that you have 200 grams of that sample, and the molar mass is 100 grams, then you would divide 200 by 100 to get 2. From there, you would take this empirical formula, say that this was the empirical formula, multiply it by 2, you would get x sub 2, y2, or y4, z6. So x2, y4, z6. So that would be your molecular formula. The most important thing about stoichiometry is the fact that is those conversion factors. Those conversion factors are very, very important for this. So let's just review those one more time. We have mole, gram, mole. But there is no gram. We have atom, mole. We also have molecule mole, which you didn't talk about. However, molecule mole uses the same Avogadro's number, 6.02 times 10 to the 23rd molecules in 1 mole. Thank you, everybody.